PdV Work. This is another video on thermodynamics lecture series. If you are interested in the topic displacement work done during various processes, sit relaxed, make yourself comfortable, watch, enjoy, and learn. Over to the topic now. Earlier, we discussed the displacement work during a process is given by the formula integral PdV, and hence the work is also called as PdV work. We also discussed in order to integrate PdV, we need to know the relation between the pressure and volume. Now, in this video, we will derive expressions for work done during different processes which a thermodynamic system may undergo. Totally, there are 5 processes. One is constant pressure, 2 is constant volume, third one is constant temperature, fourth one is polytropic process, and the fifth one is a reversible adiabatic process. The first one is PdV work done during a constant pressure process, which is also called as isobaric process. To represent a process in a graph, we consider a PV diagram. So why PV diagram? Because displacement work is equal to integral PdV. That's why we use a PV diagram. And a system is initially at state 1 and it undergoes a change of state, or it has undergone a process and reaches the state 2. The change of state is completely defined. And what is that complete definition? The change of state occurs at constant pressure. That's why the process is a constant pressure process. And remember, PdV work is equal to the area of curve area under a curve in a PV diagram. And this is represented like this. Now, what is the expression or formula to find PdV work during isobaric process? For that, consider the work done equation integral PdV, and it is integrated between the limits V1 and V2. Since it is a constant pressure process, P is taken out of the integral, and that gives W122 is equal to pressure multiplied by difference between the final volume and the initial volume. So this is the final expression to calculate the work done, that is PdV work done during a constant pressure process. The next one is constant volume process, which is also called as isochoric process. The representation of a constant volume process in a PV diagram is like this. So initially at state 1 and final state is 2. The path is completely defined. That means volume remains constant during the state change, and hence the process is called a constant volume process. And work done equation is our integral PdV between the limits V1 and V2. Here volume is constant, therefore V1 is equal to V2 and hence W1 to 2 is equal to 0. Displacement work done during a constant volume process is equal to 0. Now we will derive an expression for PdV work during constant temperature process, which is also called as an isothermal process. Remember, one needs to know the relation between pressure and volume in order to integrate PdV. For that, in, a, in an isothermal process, we make use of ideal gas equation, which is PV equal to mRT. And it is a constant temperature process. This T is constant and hence we can write PV equal to constant C because mass and the gas constant are constants. T is also constant, therefore we are using some other constant C. So what is the C? C is equal to mRT. Now in a PV diagram, consider a system is initially at state 1 and it undergoes an isothermal process and reaches state 2. So hyperbolic process. And the area under this curve in the PV diagram represents the work done. To find the expression for this work done, one need to consider the relation integral PdV between the limits V1 and V2. We know PV equal to constant, that implies P is equal to C by V, and this PV equal to constant can also be written like this: P1 V1 is equal to P2 V2, and from this we can substitute C equal to P1 V1. Therefore, instead of P, we can substitute P1 V1 divided by V. That's what being given here. So what is this? Instead of this P, we have substituted here, and instead of this C, we substitute this. So P1 V1 divided by this V. And this P1 V1 is equal to constant. Therefore, we can take this one out of the integral. What is remaining is integral dV by V between the limits V1 and V2. Upon integration, we will get this. So this formula can be altered. What is that alteration? Instead of V2 and V1, we can use pressure. For that, we need to know the relation between pressure and volume during an isothermal process. So what is that? Using P1 V1 equal to P2 V2, we can write V2 by V1 equal to P1 by P2. So this V2 by V1 in work done expression can be replaced by P1 by P2. So which gives you, so both are correct. Also, what we can write is, we know PV equal to mRT, therefore P1 V1 equal to mRT1, P2 V2 equal to mRT2. Of course, T1 is equal to T2, and hence instead of P1 V1, we can write mRT. So instead of P1 V1, we can write mRT. You can use any one of these three expressions in order to solve a numerical that involves a constant temperature process. So what is the displacement work done during a polytropic process? The pressure relation in a polytropic process is given by P V power n is equal to constant. The representation of a polytropic process in a PV diagram is like this. Initially at state 1, and the system undergoes a polytropic process and reaches state 2, and the area under the curve in this PV diagram represents the work done. And to find the formula for this work done, we need to consider integral PdV. And in order to integrate this, we need to know the relation between P and V. And that relation is given by PV power n equal to constant, which can be written as P is equal to C divided by V power n. Also, using this PV power n equal to constant, we can write P1 V1 power n is equal to P2 V2 power n. From this, we can write C equal to P1 V1 power n. Now, we can substitute instead of this P, C by Vn. Instead of this P, we can substitute C by Vn. And instead of this C, substitute P1 V1 power n. So that is what given here. So this P1 V1 power n is given by the C. And this C comes from here. And this V power n is here. And of course, instead of this P, we are substituting this. This P1 V1 power n is a constant. Therefore, in the integral, we can take this P1 V1 power out, and upon integration, we will get this one after substituting the limits. We can simplify this expression. What is that simplification? The expression we derived earlier is written here again. And of course, we know P V power n equal to constant, which is equal to P1 V1 power n, which is equal to P2 V2 power n. Now, instead of this P1 V1 power n, we can substitute C. On substitution, we get like this. So instead of this P1 V1 power n, instead of this, we substituted this C. Now multiply this C into the parenthesis, we will get like this. Again, instead of C here, substitute P2 V2 power n, and instead of C nearer to V1 power n minus 1, substitute P1 V1 power n. Upon simplification, we can cancel V2 power n and V2 power minus n, V1 power n and V1 power minus n, which gives us the expression W122 is equal to 1 by 1 minus n to P2 V2 minus P1 V1. So that is rewritten here after changing the order. So what is here? Here it is 1 minus n, but here it is n minus 1. How this change is possible? Here it is P2 V2, but P1 V1. I hope this is self-explanatory. This expression can also be modified. In order to modify that, I'm going to take this P1 V1 as a common one. So this expression can be written like this. Now, instead of this P2 V2 or V2 by V1, I can substitute. Then what is that? From this, we can write V2 by V1 is equal to P1 by P2 raised to the power 1 by n. Now, instead of this V2 by V1, substitute this. That means bring this one over here. We will get this one. Upon simplification, it gives you a relation like this. So this is the final expression to calculate what is the work done during a polytropic process. Of course, this equation is written in red color font, meaning it is enough if you remember this formula in order to solve problems that involves work done during a polytropic process. So we can use this formula and also this, both are correct. What is a PdV work during a reversible adiabatic process? The pressure volume relation in a reversible adiabatic process is given by PV power gamma is equal to constant. It is very similar to the polytropic process relation PV power n equal to constant. The only difference is the index of compression or expansion. In polytropic process, we used n. In reversible adiabatic process, gamma. Therefore, we can use the same relation which we derived for a polytropic process in a reversible adiabatic process also after substituting gamma instead of n. Before looking into that equation, first we will try to represent this reversible adiabatic process in a PV diagram. So initially at state 1 and it reaches state 2 and the area under the curve in this PV diagram represents the work done and the expression for work done after replacing n with the gamma is this. So this expression we derived in a polytropic process. Therefore, no need to redo that one again. And what is this gamma? Gamma is equal to Cp by Cv. What is the Cp? It's a specific heat capacity at constant pressure. Cv is the specific heat capacity at constant volume. Now, we are going to plot work done during a general process PV power n equal to constant for various values of n and study how work done changes when the value of n changes. Initially, Consider a thermodynamic system at state 1. It undergoes a process wherein pressure equal to constant and reaches state 2. The same system can be taken to another state 2 using a different process, and during this process PV equal to constant. Similarly, we can take to another state using PV power 2 equal to constant, and PV power 3 equal to constant will take the state to some other state. Likewise, we can keep on increasing the values to 4, 5, 6, 7, 8, and you can stop at infinity. PV power infinity equal to constant. Now what we are going to do now is, in the first process, n equal to 0. What is this n equal to 0? Here PV power n equal to 0. If you substitute 0 for n, then V power 0 equal to 1, which gives you pressure equal to constant. Therefore, when n equal to 0, it is a constant pressure process. Similarly, when n equal to 1, it is isothermal process or constant temperature process. When n equal to 2, it's a polytropic process. N equal to 3, again it is a polytropic process. And if you keep on increasing and reach a value of infinity, PV power infinity equal to constant, here volume is constant, V power infinity. So when n equal to 0, constant pressure, n equal to 1, constant temperature, n equal to infinity, constant volume process. The in-between processes are polytropic. Now, this discussion is represented here. Constant pressure, constant temperature, and constant volume. And where this reversible adiabatic process lies, it depends on the value of gamma. Remember, for a reversible adiabatic process, PV power gamma equal to constant. The value of gamma for air is 1.4. 1.4. So again, it is something like a polytropic process where gamma equal to 1.4. But we don't call that as a polytropic process, we call it as a reversible adiabatic process. And what is the value of n in general for a polytropic process? It ranges between 1.1 to 1.3. Now consider the work done during these different processes. Remember, work done under a curve represents, the area under the curve represents work done. And in this PV diagram, consider the constant pressure process. The area under the graph represents the work done. Similarly, consider the process PV equal to constant. The area under the graph, under the curve represents the work done. Obviously, work done during constant pressure process is greater than work done during PV equal to constant, that is isothermal process. We can infer this one directly from this graph. So what happens? Here n equal to 0, here n equal to 1. So when the value of n increases, when the value of n increases, work done decreases. This is what reflected in further things. When the value of n is increased to 2, work done further decreases. When the value of n is increased to 3, work done further decreases. And finally, when the value of n is equal to infinity, work done is equal to 0. So that is what given here. Work done during the process decreases as n increases. In general, a thermodynamic process is represented by the relation PV power n equal to constant, and when n equal to 0 it is constant pressure, and when n equal to 1 it is constant temperature, and when n equal to infinity it is constant volume process. And for a reversible adiabatic process, we don't use PV power n, we use PV power gamma equal to constant. That gamma value is 1.4 for air. And the value of n usually ranges between 1.1 to 1.3 for a polytropic process. Now, the takeaways from the lecture: displacement work done during various thermodynamic processes. Of course, we derived the formula for work done, that is displacement work done during the various thermodynamic processes. It is given in the form of a table here. To solve numerical in thermodynamics, one needs to remember all these. In addition to the expression for work done, a pressure volume temperature relation for various processes are given here. One need to remember these relations also. Thank you.